Hello, welcome to a video on projectiles. I'll start off, I think I'll be able to cover two problems in this, and both of them are pretty much the same. These are the conditions where the initial velocity for the horizontal direction is 0. So I'm going to show you two problems that use that condition. So if you look at this problem right here, we have a ball and it's being launched off a cliff. We don't know the height of the cliff, which is what we're going to solve for. We do know the range, and we know the launching velocity. So let's organize our information. So first of all, we know that this is horizontal, which means it's all x. Actually, I'm going to make that darker. There we go. So when it says horizontally, that's our keyword. This is also our horizontal. Another really important note is to know that our initial VI will be 0. And that's because there's no angle here. It's not moving up at all. The other information we have is acceleration. This is being thrown. So we can automatically make the assumption that it's 9.81. And we also can automatically make the assumption that the acceleration is negative. Lastly, the other piece of information we have is our range, our delta x, which is 36 meters. So our question is, how tall is the building? What's our delta y? How tall is the building? Okay, so as a quick review, recall that any sort of x motion will be modeled with the x equation, like this. This is the only equation we can use for x. And then, of course, we have many different equations we can use for y. And remember that the key to solving these problems is time. If we know time in one direction, we can do it in the other. So time in x and y are related. And let's just choose initially that I want to use this equation for delta y. Now I like this equation for delta y because it does have a time component which we can relate to each other. So if you notice what I have here, I have delta x, which is this one, and I have vx, which means I can solve this one for time, and that says how long it takes to go this 36 meters. But as it's going 36 meters, it's also falling, so they share the same time. So in other words, I could solve for time here and then plug it into this. My mistake. Okay. So let's go ahead and do this. So that means that this will be 20 meters per second equals delta x, which is 36 meters, divided by t. T will be, so 20 divided by 36. I'm sorry, it's 36 divided by 20. So to solve this, you have to do 36 over 20, which equals 1.8 seconds. Like that. So that's the time it takes to move from here to here. And like I said, as it's moving this way, it's also falling. In fact, that's what this combination of, this is what this dotted line represents, is moving in two directions. So now I'm going to figure out delta y. So this is the initial velocity for the y, recall, is 0, so this whole term goes away, which is really nice. So then we're left with a nice easy equation. Well, by easy I mean more straightforward. Seconds. It's an s squared. So what we have is 1.8 squared, 9.81, and 1/2. The final answer is negative 15.89 meters. Now, it's negative because the object is falling down. But technically, what is the height? It's 15.89. We usually just say that the height is the value, not where it went, like this. So this would be sufficient for the answer for that. So this is how you solve that. Now you can use a different equation to solve, this delta y, but the beauty of using this one is this term goes away and you have it related to t. You can use the other two kinematics, but you need the final velocity, which we'd have to solve for in the y. We don't have that, so we don't have this in the problem. So it's not helpful. But let's take a look at another problem that's very similar to this. Okay, say if this plane is moving, so we have that 120 meters per second, and it's not very clear in the problem because this is a video problem. But in the video, if you see the slides, this is moving horizontally, so this corresponds to a Vx. And we know the altitude. If they refer to altitude, they're referring to this right here, like that. Okay, that's this information. And we already organized this one. And the question is how far down range. So range represents this piece right here, x. So again, this problem looks very vacant, but I'll even organize it in terms of x and y, because sometimes it's a lot easier like this anyway. And as always, remember that x only has this equation to work with. We don't know what the range is. In fact, that's what we're solving for. We do have Vx 20. Remember that I don't put the indices on this because this is the same value throughout the whole motion. And we don't have time here. On this side, we have the initial velocity of the y is 0 because it's not moving up or down to begin with. It's staying horizontal. We have acceleration. This is not given in the problem. Remember, acceleration is assumed when you have stuff that's going or moving in the air with no propulsion. We don't know what t is. Maybe we could find that out. But we do have delta y. Like that. So when I look at this section here, I can actually use this kinematic equation. So it's a trend that I like this one for solving these horizontal problems. This is the y. Keep that in mind. Because generally, this term goes to 0 because our initial point is right there. Our initial point is not moving up or down. So actually, I have delta y, I have a, I could solve for t. Then what I'm going to do is take t and plug it in there. So here we go. 750 meters. I'll make that negative because it is falling. So let me just throw that in there. 1/2 a t squared. Solving for t squared. Now you might recognize again that these do cancel because they're going the same direction, so that's okay if you see that shortcut. So I'm going to do the math real quick. 750 times 2 divided by 9.81. Remember, you have to square root this answer because we don't want t squared, we want t. So when you do that, you get 12.37 seconds. So that's a pretty long time. So that's the time that's here. And recall, if I know how long it takes to drop, I know how long it takes to go here. So in other words, these times are the same. So here we go. Then we can do this equation, which is solving for x. And I'll plug that in. So Vx is 120 meters equals x over our time, 12.37 seconds. So Vx times t equals x. So Vx will be 120 meters times 12.3 seconds. So we're going to get a pretty large number, but this plane is going very fast and it's falling for a very long time. This looks great. 1484.4 meters. So that would be the range of our box for this type of problem. Okay, so I'm going to use the rest of this time to set up the next problem, but I'll probably need a second video to finish that up. So let's do that. Here we go. So now we're going to do a angled problem. So no longer is our initial velocity 0. We have to think about that. This is a pretty standard problem. So here's the problem. It's basically doing one of these, right? We can continue this. And the question is how long, how high, how far. So how high? This is our delta y. How far? Delta x. Then t, how long. Okay, so as always, when you have something like this, we need to break it down. And the first thing we need to do before we even begin thinking about solving the problem is breaking down our velocity into the x and y components. We're going to do that by solving a triangle, because basically this velocity here, and I'll do the work up here, is 18 meters per second, which represents the hypotenuse of our triangle. And we have an angle of 47 degrees. So what we want to do is break down our motion into just one line components, x and y, like this. And again, the reason why we do this is because we can only use our kinematics in one dimension. There's no two-dimensional kinematics. So we need to separate our motion. So I'll do that. So Vx is going to be the hypotenuse times cosine of our angle. Angle. And this is going to be hypotenuse times sine of the angle. Now, once again, as always, I am using trig to solve this. You can convince yourself that this is an adjacent opposite hypotenuse, and I'm solving the adjacent here and the opposite here. So I am doing these quickly because I assume you're comfortable with recognizing how these work. Let me do both of these calculations. Okay, so the sine component is 13.16 meters per second, and the x component is 12.26 meters per second, like that. Now this will represent the initial velocity of y. Remember, y changes the whole time. And this represents Vx. And this stays the same no matter where we are. So those are the two most important things about our problem. This is a 2, by the way, 2.6. Okay. I'm sorry, I rounded that wrong. This should be 2.8, not 2.6. Let's stay consistent. So I'll rewrite these. 2.8. Great. Okay, so now that we have some information, let's start off with how long the ball is in the air. And remember, we're not going to use this 18 anymore. That's not useful. So I know the initial velocity of the y is 13.16 meters per second, like that. And I know that my final point, if it ends and starts in the same point, is also this value. That's an assumption we can make. I'm going to put Vy right here. And this is a Viy, an initial. Now I didn't put final because we can pick our final point. We can also assume that the top Vy up here is 0, like that, which is useful. And our Vx is the same, so I'm not going to label it because it literally would be the same numbers across, like that. So I have enough time to solve for the first part. Let's solve number 1a. What is the time the ball is in the air? Well, notice I have a change in velocity. And, as always, always, we have a in these problems. I'll box that, why not? Because that's information we have. So, I can choose my initial velocity to be this one right here, 13.16. And then I can choose my final velocity here, and that will give me the total time this ball was in the air. And then I have my acceleration, so negative 13.16 meters per second squared equals positive. Now these do not cancel out, so just a warning, people say, well, isn't it 0? It is not. Mathematically, these actually add because this becomes negative on the opposite side. So 13.16 plus 13.16 divided by 9.81. Perfect. We have 20 seconds left. The answer is 2.68 seconds, and that's the total time this is in the air. I'll solve the next two parts in the next video.